Hello everyone. Today we are going to give our term paper presentation which comes under deep learning course which is taught by Dr. Aditya Nigam and Dr. Arnav Bhavsar at IIT Mandi. So now let me introduce you to the topic of presentation which is Mega-TTS 2 boosting prompting mechanism for zero shot speech synthesis which is written by Jiang et al. So now let me give you a brief overview of our topic, what we have done in that. So the next slide is introduction, which is presented by me, Shiv Bhaskar, and the motivation is behind this topic will be explained by Himanshi, and the key challenges will be given by Samiran, and the model architecture will be explained by Pradyumn, and the experiments and results will be shown by Siddharth, and at the end the topic will be concluded by Shweta. So now I will give you a brief introduction about the topic and motivation behind this topic. So as you can see in today's world, like in our daily lives, we use like basic things which is Siri, Alexa, audiobooks, and language learning apps. So in which the basic system is text to speech. All of them are relying on TTS. So today nowadays users basically focus on the procedurally rich data. They want natural expressiveness, personalized things, and they don't want big data to given input as a input in system, but they want specific short data, and then they want a rich data output. So, like in the next slide, I'll give you some brief introduction about what is TTS. So, TTS is a task which is converting an input of sequence written text into speech waveform. Like traditional systems need hundreds of minutes in old times to record speech from a professional voice artist, make them costly and rigid. In contrast, Zero shot aims to generalize new voices with minimal data. Like in short data, we can generate a rich output. So for that, we use zero shot speech synthesis. So now the next slide will be explaining that what is voice cloning and what is zero shot TTS. So basically, voice cloning is a subtype of TTS where the output should sounds like specific target speaker. But in goes zero shot TTS goes beyond one step ahead. In that we basically generate a speech brand new speech voice which is after coming a short reference given by us as an input and generate a rich output like. And why does it even matter? Because it sometimes saves our data compared to traditional voice cloning pipelines and big we don't need to create big pipelines for that. We just need to give some short synthetic voice, and even speakers low resource language also can work for individuals who lost their voices, and we can generate their highly prosodic rich voice as an output. So in the next slide I'm explaining that why is zero shot TTS challenging. As we can say that unfortunately in existing zero shot methods we have two problems which are prompt length limitation. Many systems accept that only a single sentence as a reference, which may not capture a speaker's full vocal range. Like it can't capture all the uh, procedurally rich things which comes under timbre and um, procedurally rich data like rhyme, stress, emotions, pitch, and many things which comes under prosodic. So, and this makes it hard to control style and expression as independently. Like there are some limitations also when it comes to the result. So, and Mega-TTS 2 tackles both the issues of by redesigning the prompting mechanism, allowing richer references signals and timber from prosody. Then and the next thing which will be explained by Himanshi, that the what is the motivation behind this topic and how it goes. So Himanshi, now it's over to you. You can continue from here.
Okay, thank you, Shiv. So now we will discuss about the motivation behind using the Mega-TTS2 model. So basically, as Shiv discussed about zero-shot TTS. So basically, what is zero-shot TTS? In this, we can make a computer in someone's voice by just giving a short audio clip, and it's very super fast and doesn't need a ton of data, because traditional TTS models it requires a large data set and it requires a large time for training, computation cost, which is not good. And by using zero shot TTS, it reduces a lot of data, so which is very awesome. But here is a problem. The problem is that even though we copy a voice, it still doesn't sound truly like a human. It often sounds a little bit like a robotic or like a dull. And what's the reason behind this? Because most systems only use one sentence to learn how a person talks. And let's be honest, one sentence is not enough to understand someone's full voice, their tone, their personality. Also, the system can't really tell the difference between the timbre and prosody. So, what is timbre and prosody? Let me explain. Timbre is like what the voice sounds like, and prosody is how the person is speaking, means their emotions, whether they are like excited, sad, calm, or angry. These two things which we use, which is voice and emotion, get mixed together. So if you try to change the emotion, the voice might be changed, and that's not good. So for example, now imagine you want the same voice to speak happily in one case and sadly in another case, but still sound like the same person. And with the current system what we are using, like a zero TTS, that's really hard to do so with this. So researchers came with idea of the Mega-TTS2, which was created for resolving these issues. First one is that letting the system listen to multiple sentences, not just by one, so that it can understand the voice better, it can identify the voice identity better. Second one is that it separates the person's voice identity and their emotional or speaking style, so you can control both individually. Third one is that making the final speech more real, more emotional, and more flexible. Basically, in simpler words, if I have to explain about Mega-TTS2, is that it helps the voice cloning to go from sounding robotic to sounding like a real person with real feelings. And now, moving forward about the key challenges of zero shot TTS and Mega-TTS2, it will be discussed by Samiran. So it's up to you.
Thank you, Mansi. So, so our next section is on the key challenges in zero shot details and what Mega-TTS solves. So this section sets up the main problem. Zero shot details is promising, yes, but existing models face real limitations. They struggle to sound natural or expressive, especially when given very little input. Mega-TTS tool was designed specifically to address these issues and improve voice cloning quality. So the main challenges in previous zero-shot TTS models was that earlier models mostly used only one sentence to understand a speaker's voice. But that's just not enough. It doesn't capture the range of ways in which we naturally speak, like changes in tone, pace, or emotion. Another issue is that they combine timbre and prosody into one representation. Timbre is basically who is speaking, and prosody is how they speak. So mixing them together makes it harder to control the speech output. So the result ends up being robotic or less expressive, or you can say less human-like. So going into what is timbre and prosody. So to clarify that, timbre is basically what makes your voice sound like you. It comes from physical features like your vocal cords and throat, and it stays constant whether you're happy or sad. Prosody, on the other hand, is about emotion and speaking style. Things like pitch, rhythm, and stress. It's what tells us whether someone is excited or serious. Even with the same words, like prosody can totally change the meaning or emotion. So why is using only one sentence a problem? So if we use only one sentence as a prompt, we miss out on all the variety in a person's speech, like different emotions or tones and ways of speaking that the speaker shows in his speech. So that's why the output ends up sounding either too flat or too uniform. It makes it sound robotic. So there is just not enough information in a single sentence to build a natural sounding voice. So how does Mega-TTS to address these challenges? So Mega-TTS 2, what it does is that it fixes this by using multiple sentences as prompts. This gives it a better, fuller picture of the speaker's voice. It also separates timbre and prosody using a smarter neural network design. This means that we can now control the speaker's identity and their speaking style independently. The result is speech that's much more realistic, emotional, and flexible. So going on to the next section, we have Mega-TTS2 model architecture, which will be presented over by Pradyumn. Over to you.
Okay, so thank you, Samiran, for giving us such a elaborative idea about the key challenges that we face in zero-shot TTS. And now I am going to discuss about the main section, which is basically the architecture of the model, which we can say is the heart or core of this presentation. So, so first, I would like to start my model with a what goal we are looking for. So in zero-shot TTS, we want a model to speak sentence using a voice it has never seen before, and just a short with a just a short audio prompt. So to do this well, how we are utilizing Mega-TTS to that separates the speech because how it is approaching. So I would like to go to the next slide, which will be explaining the whole architecture of the model. So yes, so as you can see in this diagram, we have the whole architecture as an image presented to you. So in this, you can see uh, that there are three different sections. So one is ZC, another one is ZT, and the third one is the ZP. So what are all these? So first is basically the content. So what is basically the content here? So these are the phonemes, so as a data. Second is the timbre. So timbre basically, as my friend Somiron explained, is the speaker's voice or the speaker's identity. So who is saying it? And the third is the prosody. So third is basically how does it being said. So basically, then it includes pitches, energy, duration to say each phonemes, all those things. And how this separation is done. So this separation is done with the help of three encoders. So as you can see in the image, on the top, we have a multi-reference timbre encoder, which is our most important thing, which I'm going to discuss in my further slides also. In the center, we have a content encoder. And the third is the vector quantized encoder. Okay. So multi-reference timbre encoder, as it is named, it take cares of the timbre, and basically it gives the output ZT, which includes all the timbre data, which is generated from the MEL spectrogram of the multiple sentence prompts. Then then is the second content encoder, which is basically taken from the phonemes, and the third take cares of the prosody. Okay. So now let's look how these one sentences are, how these data set are created. So as you can see in the initial section, in the input section, that in prosody we have a just one image of a MEL spectrogram, while in case of timbre, we have a multiple sentences as a prompts. So why this is so? So the exactly reason behind this is that for prosody, we basically use a data which we want to reconstruct. So here, basically, we have an autoencoder, and we want to just focus on that particular data set which we want to reconstruct. While in case of timbre, we consider all the data sets which can be used for generating the timbre, or these dataset will refer only to the voice identification. So this will help us to identify what voice will be utilized. So now we can move on to the next slide, where basically I am going to tell you the most important thing, which is compressive acoustic autoencoder. So basically, it's very simple to understand. It is based on the autoencoder model, where basically we are giving input as a data in a prosody, and parallelly we are also giving input of the multiple sentences, multiple prompts of a single voice which we want to copy, and then we are expecting an output from a decoder, which will combine all those things later, and then it will give us an output which will be very similar to what input of ground truth was. Okay, so and then a reconstruction loss will be applied between them, and this is how the whole idea will be considered. Okay, so as I think I have very clearly expressed my idea that Mega-TTS2 goals is to compress the speech into basically three separate representations, which are ZT, ZC, and ZP. And then it will combine and it will give it to the decoder. So first, basically, all the audio files will be converted into a MEL spectrogram, and then these spectrogram will be given to generate our data set. In the output also, we will have a MEL spectrogram. In the previous slide, as you can see, we have a MEL spectrogram, and then it can be generated to a visual audio or this. So now moving on to the next slide, we will be discussing about what is multi-reference timbre encoder. So this is basically the main thing that they have created and that they have added here. So how timbre is basically given. So as I have explained you earlier, that the multiple sentence for reference will be given in the code, sorry, as a data set to the model. And in the model, we basically have a encoder model, which will be having a multiple layers, and each layer will be having a conv 1D, layer normalization, and GELU activation. So basically, what conv 1D is doing, conv 1D is doing is here basically, it is taking the images of the MEL spectrogram, and then it is downsampling it, or basically featureizing it into special vectors which can be help us which can help us to identify the voice identify and the voice identifications. And once these are identified, then a layer normalization is done, which is basically making it a zero mean and unit variance. And after every that, a nonlinear function, this is GLU function, somewhat similar like ReLU function, but it is more smoother than that. This will be used. So yes, this is the whole procedure, and that is how ZT is generated. And once a ZT is generated, then using an attention mechanism, we are combining our ZT with the content. So here, what basically we are doing is we are successfully able to classify our data set into, or our whole problem into two sections, which earlier zero TTS models were not able to do. Like here, we have completely classified our reconstruction model, uh, that is prosody. And apart from this, we have classified timbre and content. So, and then we merged it finally into the decoder. But before merging all things into the decoder, we use attention mechanism to combine the content with uh, the timbre. So basically, the ZC, as if you remind about the previous architecture diagram, so the ZC that is being generated from the, yes, in this diagram, as you can see that the ZC that is generated from the content encoder will will be a query, and the ZT will be a key and a value. So like each embedding will be combining with the each timbre, and those which will fix perfectly with other will be perfect for us. And that's how a suitable voice for a particular content will be defined. And similarly, once it is passed to decoder, then we will get the final output. Yes, now we can move to the another side, which is basically our prosody latent language model. So basically, this slide focuses on about the PLLMs. And once we have like learned how someone speaks across multiple sentences, we want to model how their prosody changes over time, like when they emphasize words or change pitch. So PLLM basically is a language model that operates on a prosody codes. And here, like now, what the process is that basically from multiple training sample, the model extracts ZP and ZC for each one. And then these are concatenated to form a long sequences, preserving the system boundaries, sentence boundaries. And duration and some duration of information is also added so that it becomes prosodically length and we understand like how each phoneme is given. Okay. And then the PLLM predicts the next prosody token in the autoregressive way, one step at a time. Okay. And then this is the way like how the all speeches are naturally evolved. So to avoid that sudden transition. So if we go to the next slide, we will understand like basically like if we want to extract two sets of prosody codes, so one from the target speaker and another from the different speaker and emotions. So basically we decide a factor, a gamma, that basically help us understand. So let's say suppose if a person want to say that I love pizza, and there can be two emotions in that. Maybe it's an ideal example, so it can be a happy emotion or a sad emotions. So we can, using our that prosody factor, we can fine tune our, we sorry, not fine tune, we can basically tune the emotions of the sentence. So I love pizza can be said in the person's voice in a sad tone. On the other hand, voice like on the same sentence can be said in the sad tone. So this was the all about the architecture of the model and the whole idea behind how the model works. And now I would like to invite Siddharth, who will give you a brief idea, who will give you a good idea about experiments and the results that are being done on this model.
Yes, thank you, Pradyumna, for explaining the model. Now we will look at the experimental setup. So the authors have designed the experiment. So first they have used a they have created a training data. So the authors trained all their models on LibriLite dataset, which consists of about 60,000 hours of unlabeled speech from LibriVox audiobooks. And all the samples were at 16 kilohertz frequency. And these audio chunks are transcribed using a pre-trained speech recognition model, also known as automatic speech recognition models, and phoneme alignments were created using an external tool. So to name one of the tool, Kaldi is also one of the great tool for uh, al alignment of phonemes. Now, the hardware setup. So basically to train our model, so basically we did training in two stages. And the first stage, the training of acoustic autoencoder as mentioned by Pradyumna. So it was trained using four NVIDIA A100 GPUs and with a batch size of 48 sentences per GPU. In the second stage, the prosody latent language model PLLM and the duration model were trained on 8 A100 GPUs with a batch size of 4,000 tokens per GPU. And now the training was run for 6 lakh steps in stage 1 and 3 lakh steps in stage 2. And the hyperparameter used for this training was one of the widely used hyperparameter, that is Adam optimizer. And uh, for converting MEL spectrogram back to audio, we need a vocoder. So in this case, we have used, the authors have used a pre-trained hi-fi GAN vocoder. And generally the baseline models like Fast Speech 2 um, on, uses GAN vocoders. Now, uh, now we will discuss the evaluation matrix. Uh, So basically, we can classify this in two subcategories. One is objective matrix and subjective matrix. So first, we will discuss the objective matrix. So uh, it consists of three part, basically word error rate and speaker similarity using WaveLM speaker verification model and dynamic time wrapping for pitch prosody accuracy. And the next thing, that is subjective metrics. It is based on mean opinion score test, and it is done on mechanical Amazon Mechanical Turk, covering both audio quality, QMOS, and speaker similarity. That is SMOS. And each example was rated by at least 20 listeners. So now we can discuss results. And so results we are discussing for zero shot synthesis, and the author compared their method to two baselines. So basically, the two baseline are, the first is the fast speech 2 that is represented as baseline here, and another model is Valley model. So Valley is a leading zero shot TTS model, and a fine-tuned baseline model is the fast speech 2 with GANs, and where GAN is a vocoder. So they have tested how well each model performed at the length of reference prompt, and we have increased the audio from 3 seconds to 300 seconds and tested our results. As we can see, like for each models, baseline, Valley, and the author's model, that is Mega-TTS 2. So they have done the testing for 3 to 300 seconds of audio input. So we will discuss each things one by one. So Mega-TTS2, the model prepared by the authors, have achieved lower word error rates and higher speaker similarity than both Valley and the fine-tuned baseline model, that is fast speech 2, especially when more prompt audio was available. So we can see a significant drop in word error rate when the audio duration is increased for our uh, Mega-TTS2 model. Next is, we can also see an example for an instance. With 10 seconds of prompt audio, Mega-TTS2 got a word error rate of 2.28% and a speaker similarity of 0.905. And whereas with 300 seconds, we can see the speaker similarity has increased to 0.932 and word error rate has dropped to 2.23%. Now, speaking about prosody transfer. So the authors have also evaluated the ability to transfer expressive speaking styles, that is nothing but prosody, from one speaker to another. So their method enabled controlled style transfer, such as making a speaker sound happier or sadder while keeping their original timbre. And Mega-TTS 2 has also outperformed models like Copycat and others in prosody transfer tasks based on both objective and subjective metrics. So we can see the results, the graphical result, the visualization is also presented. And uh, now we will come to next section, that is ablation studies by the authors. So this study shows that the ablation experiment to test the importance of each component, like multi-reference timbre encoder and the VQ prosody encoder. So results showed that removing these modules lead to a clear drop in quality and speaker similarity, confirming that disentangling timbre and prosody is crucial for high performance. So we can conclude that disentangling timbre and prosody, so both should not be kept together. It should be separated, and it is crucial for high performance. And this was also discussed in the initial part, and it was the initial objective as well. So to sum up, the Mega-TTS2 model, as presented by authors, demonstrates strong performance in both zero-shot speech synthesis and prosody transfer. And their approach of separating timbre and prosody and using multi-sentence prompt leads to more natural and flexible voice synthesis, outperforming current state-of-the-art methods. So now I would like to invite Shweta to conclude uh, this presentation. Over to you.
Yeah, thank you for joining our presentation on this paper. So to conclude this, Mega-TTS2 revolutionizes zero-shot and text-to-speech, which clones voices using just a 10-second audio sample without training, as noted on slide 6. It introduces a generic prompting mechanism, overcoming the limitations of single sentence prompts in older systems, and as shown in slide 10, making clone voices more natural and expressive, as per slide 8. Mega-TTS 2, its key innovations include a comprehensive acoustic autoencoder that separates timbre, the speaker's vocal identity, from prosody like emotion and rhythm, as per slide 15, ensuring emotional changes don't alter the voice. Its multi-reference timbre encoder uses multiple sentences to capture vocal nuances, as on slide 17. While the prosody latent language model enables controllable expressive speech, as per slide 16. Prosody interpretation blends emotions like mixing happiness and sadness while preserving identity, as on slide 19. Imagine a virtual assistant sounding cheerful for good news, which enhances user engagement. Finally, Mega-TTS2 outperforms baselines, achieving a 2.23% word error rate and 0.932 speaker similarity on LibriSpeech, surpassing fine-tuning methods as per slide 22 and excelling in prosody transfer on the ESD dataset as on slide 23. In summary, Mega-TTS Mega-TTS2 sets a new standard for zero-shot TTS with its natural controllable synthesis. So on behalf of my teammates, thank you so much for listening to us, and thank you.
Thank you very much. And we would like to uh, thank all the members whoever gives presentations. Thank you.
Yes, thank you.